Hi, my name is Andrew McLaren, and I'm going to help you today with when you have two ropes holding an object up. They may be at different angles and trying to figure out how they relate to each other in terms of the amount of tension that each one is getting. So by the end of the session, you should be able to solve any problem and any component in this situation. We're going to look at a couple different problems to get you to do that. So we've got this first one that I'm going to go over, like I've got all the work done, and we'll go through step by step the logic in that. It's a little bit more difficult than other problems because alpha and beta, they're not relative to the x-axis, one's relative to the y. So you have to be a little bit careful there with your triangles that you're going to end up drawing. Then there's a simpler problem that I'll go through step by step and talk about the logic on that. That should reinforce some stuff that I'm talking about before there. And then also it will be relevant for understanding these slightly different angles here when we work through that. And then we're also going to do one problem where you just have tension to the side and at a different angle. So if you have a problem that looks like any one of those four problems, by the end of this video, you should be able to solve for it because they're all essentially relating these sum of forces in the x and in the y direction and trying to think about how that relates to the movement or lack of movement. Yeah, let's go ahead and dive in. So with this first problem, I've already worked through all the work, so I'm going to just kind of explain the steps here. So when we're looking at this object here, we've got a object that is not moving. It's not really going to the side at all or up and down. So there's no acceleration, as well as there being no real velocity, but it's more important to talk about the fact that there's no acceleration in the x-axis. And so the sum of forces in the x should be zero because we know this acceleration is zero. And if we know that acceleration in the x-axis is zero, then what we can say is that the magnitude of the x components of these two tension forces are going to be equal to each other. So you can say that basically the what I would call the ft1x and the ft2x, those are going to be equal and opposite in terms of their magnitude. And the nice thing is that we have the angles here. And so we have some angles that we can kind of use in the triangle. This is typically what you're going to look at where they've got theta relative to the x. So that's kind of nice. But because we've also got this alpha where it's relative to the y-axis, what becomes the opposite is a little bit different than over here. So you can see like I've got opposite in the x-axis here and opposite is in the y-axis there. So that's going to come important when we were talking about the trig functions that we're going to use to relate these different components. But in general, the sum of x, there's no movement there. And so we can say that these are going to be opposite to each other and equal. I don't know exactly what the numbers are, but I would think of these as one of them being negative and one of them being positive. But because one is negative, one is positive, and they're equal to zero, when you put them together, you can kind of rearrange this formula. So you can bring the one of these forces over to like the other side of the equation where there's a zero, and now you're looking at two positives related to each other. So the the reason that we've got sine and cosine is because we're using slightly different triangles to relate them. If we look at the SOHCAHTOA, we've got the sine right here and the cosine for the 29 degrees. And so when we're using the 29 degrees, the opposite here is going to be talking about the y component. So if we're trying to get the y component, it's going to be related to its sine, but its cosine adjacent for it is now the x. So this is its x component in terms of a cosine function. So we can relate those two. You can kind of see the cosine here in the x now. And in a very similar way, we've got the y, just kind of the opposite here, where we've got the x and y for this blue one. You can see that sine for its opposite, that's going to be the x-axis. So if we're trying to relate the x-axis to the total tension force in this triangle, then you're going to end up having the sine. And so you can kind of see that's why we've got sine here in this system of equations, right? Likewise, we know that the two things, those two tensions, they're both pulling up, but gravity is pulling down. So I've got like the force of gravity right here, drawn in right here. And then we've got this right here is going to be that force of the tension of 2. And this is that force of the tension of 1. Now I've just kind of drawn this in, and because of the angles that they're at, I can see that the force of tension one's gonna be bigger so that it can cancel out the x-axes. So even though I don't know the exact number, I know that that's a bigger force, and therefore it's also going to be getting more of the y-axis component. Like this number, it's ft1y is bigger than ft2y. So I don't know the exact numbers, but it's not 50-50. Because these things are at different angles, we know that the y-axis is going to not be splitting like the force of gravity between the two of them evenly in terms of canceling it out. So whatever f of g is, that's going to be a significantly negative number. Then we're going to have two smaller positive numbers, but they're not the same size. So we've got the force of gravity there, and we've got the expressions that we can substitute in for the ft1y and ft2y from those trigonomic functions of those two triangles. And I'll draw those out a little bit more clearly. So if you're not sure about what's going on with those triangles, bear with me on the other problems and I'll draw them out a little bit more clearly so you can see that and redraw the triangles out. So we end up having this system of equations where it's kind of interesting, but you may not quite see it at first. But you know that, for example, right here, we've got this ft1, which is related to that, and ft2, which is related to that. So we've got these decimal points. And there's a little substitution that you can do in here using the y-axis relationship. So we knew that these were equal to each other, and we could kind of do these two different decimal points, and it's basically relating a to b. So we want to know how much of a is in b, and there was a fraction there. So we could relate these two forces through them canceling out in the x-axis and these sine cosine functions, and we can then substitute that into the y-axis. So you're kind of looking at the x-axis and the y-axis system of equations and doing a little substitution in here, if you remember that from your math classes. So then we've got the sum of y-axis stuff, but now we've got everything in terms of ft1, so you can combine like terms. So you just end up combining the decimal points from the trigonometric functions. And you should be able to solve for f of t1 relative to that gravity, which we know is the 151.9. And so then you can solve for the ft1. I got about 139 or 140 newtons for that. Now that we have ft1, you can relate that back to the sum of forces in the x-axis situation. So we've got that equation, and you just kind of plug it in, and that should tell you what the ft2 is, which I'm getting about 41 newtons. I always check if something sounds reasonable, so I wanted to plug these back in and see if these numbers worked out with the y and the x-axis, their magnitudes. And I did see that the x-axis, that the when you did sine and cosine of those two numbers with those angles, they end up canceling out. So the x-axis really does cancel out. We can see those canceling out. And you can see that in the y-axis, these two numbers add up to be about 151.9. It wasn't exact because sig figs kind of come into play with these numbers. There's quite a few significant figures on them, so it could come off if you've rounded a little bit too early. So I think I was rounding like 4 sig figs here, and that may have affected our numbers slightly, accounting for those slight differences. But if we look here, I mean, this makes sense. The 139 is this nice long force of tension 1 compared to about 41 newtons of force of tension 2. And then when these two end up canceling out in terms of the drawn triangles, which I'll do this a little bit better in the work through problem when I go through that later on, the medium difficulty. But basically these end up canceling out, and you can see that that really is equal and opposite, like what we've drawn here with the magnitudes of them being equal to each other. And that's really the trick of these problems. You want to make sure that the sum of forces in the x cancel out, and in the y, they're kind of splitting how much they're canceling out the gravity. It's hard to say exactly how much is of the two, but it is ultimately a combination of those two. And if they're at the same angle, it's pretty easy because they're going to both get half of the gravity in the y component. So that is a lot easier of math to visualize. So we'll go over that soon. So when we have two angles that are at the same angle here, it's fairly straightforward because, like what we had last time, the sum of forces in the x-axis should be equal to 0 due to the fact that the sum of forces here in the x-axis, there's no acceleration in that x-axis. So if this is 0, then the sum of forces should be 0. And we can look at these two as different triangles. So you can look at these forces like a force diagram. So if we get our little force diagram going here, we got our X and Y components. And the nice thing is that these things are actually going to be the same size. Because they're at the same angle, I can kind of draw them to scale so that they are pretty much the same size and the same angle. So we've got this blue line here. I'm going to break that down into its X and Y components. So we've got this is the force of tension 1, force of tension 1 in the x-axis, and force of tension 1 in the y-axis. And we can also do the same sort of thing here with the other green line, and it should essentially be the same numbers for all of these different positions between the two, but it's good to think about this so that you can then think about the harder problems when they're slightly different between the two. So we've got this ft2 in the x-axis and ft2 in the y-axis. Likewise, these are equal and opposite due to the fact that there's no motion in the x-axis. So if we look at the x-axis, we've got this ft1x, and then you're going to add to that the ft2x. And I really insist on doing these like as f of t, not just t, because tension should be a force. And so it just, in my brain, makes more sense to use f here as opposed to t. And also there's like period is represented by t, and like torque looks like a t. So it just gets a little confusing if you're using t for tensions like that. So we've got these two, and we know that one of them, the magnitude is negative, one of them is positive, but these are equal and opposite. And we can also then look at the y-axis. So we can say, okay, well, the sum of forces in the y-axis in a similar way should also be 0 because this object isn't falling or going up, so it's not accelerating upward or downward. And there's also this force of gravity. So there's this force of gravity that's bringing it down, so that has to be canceling out these y components, the ft1y and the ft2y. So whatever that number is going to be pretty significant in comparison to those two. I think it's going to be twice of what those are. So when they're at the same angle, these two will end up equally contributing to the positive direction. So you can think of this as your ft1y also being added to the ft2y. And then also this gravity. So gravity is just in the y direction. So it's just going to be the whole force of gravity there. And that number should be negative. And then these two are going to be positive. And just visually looking at these, they should actually have the same magnitude in terms of the numbers. So these are going to be the same number. So when we look at this problem, there's a slightly different approach that you can take here. You don't have to do quite as complicated substitutions, but it's good to like think about those as well. But the math on this might be a little bit simpler. So you can just look at what f of g is, which should be, you know, the mass times the acceleration of gravity, which is going to be, in this case, 10 kilograms times that negative 9.8 meters per second squared. And so if we're looking at that, that would be 98 newtons downward. So this force of gravity, it really is a negative 98 newtons. Sometimes you'll get this as a positive if you're looking at downward being a positive, but usually down is negative by default. So that's a negative 98. And I know that these are going to be equal to each other. Because of that, we don't have to do as quite as complicated substitutions. I can just say that the ft1y is equal to the ft2y, and therefore you can just kind of add these two up as like the same sort of thing. So you could do a system of equations trick where you're like, okay, well, I know that these are going to be equal to each other. So instead of having the same thing here twice, looking a little bit different, I can make them look the same. So it's like, okay, I'm adding two of the same thing. And so I've got 2 times that ft1y, and that's going to be equal and canceling out with this f of g, which is going to be the negative number. So we can say like, okay, this was the negative 98 newtons. These should be adding up to 0. And so I've got like 2 times this unknown variable. We could call it x if that makes it easier for you to see that. And then it's like, okay, well, whatever this is, it ends up being half of 98. So that'd be 49. So this ft1x ends up being a 49 newtons, but it's actually not negative here because it needs to be canceling that out. It's going to be a positive 49 newtons. So we know that the ft1 is positive 49 newtons. Therefore we can also say ft2y is also positive 49 newtons going upward. And we can then relate that to the triangle that we've got drawn up above here. So we're going to redraw one of these triangles. Let's do the green one because it's kind of like the default that you're used to seeing with your up and to the right. So we've got the ft2, ft2y, ft2x, and this angle of, I think what was it, 30 degrees? Yeah, it's 30 degrees. So we've got 30 degrees. This is up 30 degrees from the x-axis. And then we can relate this known quantity using that angle to the hypotenuse here. So if we're looking at this, we've got our trig functions, so, ka, toa, which I always write out that whenever I'm using them, because it's really easy to accidentally use adjacent when you're meaning to use hypotenuse. And in this triangle, we can see that the angle is here, so the opposite is there, the adjacent is here, and the hypotenuse is there. So if I want to use opposite and hypotenuse, that's going to be my sine function. So my sine is going to be opposite over hypotenuse. In this context, that's going to be sine of 30 degrees, which is equal to this ft2 in the y axis. This is definitely in the y, so I want to make sure that's clear, not looking like an x, and this ft2. And we should be able to solve for this, and we have that as a number. So sine of 30 degrees, let's just go ahead and do a little math problem there. So we've got our 30 degrees. Sine, make sure that you're in degrees, not radians, right? So that's going to be 0.5. And so we can see that this ft2 in the y is now going to be half as big as ft. So this was going to be 49 newtons. And then this ends up being twice that. So this ends up being the 98 newtons. I don't think that this is going to work out quite as neatly. Like, it's not going to be tension is always what gravity is. It's just this 30 degrees. So if we change this angle a little bit, they're going to be, this ft2 is not always what gravity is, and ft1 isn't always what gravity is. They'll depend a little bit. So we can look at that, and we can be like, okay, well, I know what this tension is. And because I know the blue triangle is the exact same number, it's also going to be canceling out like that. So we can end up kind of working through them that way and getting those two tensions. So I know that the ft1 is equal to this ft2 in this context, so that they're both going to be 98 newtons. Again, that's kind of nice if this was 30 degrees. If this was slightly different, let's just talk about really quickly if this was at like a 45-degree angle. So it's a slightly different triangle. So it's like instead of 30 and 30, these are going upward a little bit more. So the triangles are similar, but slightly different. And you can imagine that the steps are all very similar, but the exact numbers that we're going to get are going to be slightly different here. So if we've got the 45 degrees there, then it's the same sort of trig function. But sine 45 degrees is not 0.5. If we do 45 degrees, and we get our sine function on that, it's 0.707. I usually do 4 sig figs on those just because you sometimes have things that are actually 3 sig figs on these problems. I'm just doing 2, but it's good to have a couple extra sig figs on that part. So in that context, they're like the two tensions are still going up and canceling out gravity in the y direction, but what you end up getting for that final tensions there are going to be slightly different values. So if we look at that, then we can see like, okay, this is about 70% of that number. So you can do a little bit of rearranging here, and you can take 49 and divide by 0.7071, and I'm getting 69.3. Or if we're doing the sig figs on that, 2 sig figs, that'd just be the 69. So you can see that this isn't exactly the other number that we had above, but that should kind of make sense to you if we have the triangles at a slightly different angle here. Although the y's are still canceling out gravity the same amount, they're angled up a little bit more. And so there's like a little bit less in the x direction now, although they're equally canceling out, and we're resulting in a slightly smaller force of tension. Okay, so that's if you've got these two at the same angle. It's a little bit easier the substitution that you're doing here, but it's the same sort of logic. Here we were able to just relate these things to each other very directly, which is nice and simple. But we'll go over the next one, which will help you kind of connect what we did here to the first problem as well. So this is more similar to the first problem. This is nice though, because we do have the thetas are still relative to the x-axis, so we'll kind of be able to relate them through similar things for sine on x or y. But you do need to be careful with that because that's not always the case, like we saw in the first problem. But like we did before, the sum of forces in the x-axis, they should be canceling each other out. So this is not moving to the side, and it's also not going up or down. So the sum of forces in the y direction should also be 0. So that's going to be the key that kind of unites all these problems. The exact substitution that we're going to need to do here is going to be a bit more complicated than the one that we just did, due to the fact that this isn't being split 50-50 between the two. So in terms of the tension going up, there's like a little bit more on the one that's angled a little bit more up than the one that's angled to the side a little bit. So if we're looking at this in terms of the force diagram, you're going to end up having, some gravity going down. As always, we got that force of gravity pulling you downward on the earth. And then we're going to have this green. I'm going to do that kind of like here. That looks like about 45 degrees to me. And then we're going to do this at a slightly less steep angle there. And that's going to be canceling out in terms of their x-axis. So whatever this is, that should be equal. In terms of the x-axes, these things should be equal to each other. And in the y, they should be summing up to cancel out the gravity, but you can just see visually right now that the green is going to have a bit more in the y direction than the blue. So it's going to have a larger y component contributing, and we can't really say like exactly what portion it is right now without doing some substitutions. So we can see that we're writing out the sum of forces here in terms of the x-axis. Then you're going to have the F of tension 1 in the x-axis, which is this guy right here. And that's being related to the force of the tension 1. And this is going to be that force of tension 1 in the y-axis, so on and so forth. This should seem kind of familiar at this point after looking at those other previous problems. So we're going to have our 2 in the y and force 2 in the x-axis. And these things are equal and opposite to each other. So we'll have this also here. Whatever this is, one might be negative, one might be positive, but those are equal and opposite, whatever those numbers may be. Then we've also got the y-axis. So although they are adding up to cancel out to 0, we have some actual numbers here. So there is going to be that force of gravity downward. And then we're also going to have our force of tension 1 in the y direction and the force of tension 2 in the y direction. They're going to be not exactly 50-50 here, but I'm thinking that one is going to be a little bit bigger than the other, but they're going to be positive in terms of their magnitude. They should be going up. And then you've got this force of gravity that's negative and it's going downward. So this we can see is like bigger, smaller, just visually from this right here. We don't know exactly what the numbers are without actually doing some of our trig functions though. So we'll have to kind of redraw these triangles out. So if we look at the green triangle redrawn out, it's a 45-degree angle triangle. So that should look pretty much like these are the two same lengths there. It's not perfect. I never claimed to be perfect. But we've got this ft2 here, ft2y, ft2x. And if we looked at the 45 degrees angle, this is then going to be considered opposite, adjacent, and hypotenuse. So if we do so TOA, then we can start rearranging and figuring out how the x-axes might be related to each other. So if we're looking at adjacent over hypotenuse, we do that, we're going to have to do the sine as well. But if we're looking at cosine theta, that should be adjacent over hypotenuse. And we've got cosine of 45 degrees here. So in this case, the adjacent is now going to be ft2x, and our hypotenuse is the ft2. We can write out this now as ft2x is equal to cosine 45 degrees times ft2. And you can do the same sort of thing with the sine. So we've got our sine theta opposite over hypotenuse, sine 45 degrees. And now our opposite is ft2y over the ft2. So we can then rearrange that and say that ft2y is equal to sine of 45 degrees times ft2. So we've done that for the green. We're going to do the same sort of stuff, but now for the blue, they're slightly different angles, so we do need to be a bit careful here. We've got our triangle. I'm going to see if I can just copy paste that instead of rewriting it. We'll see if that works out. Hey, that worked out pretty good. So we've got our angle. I believe it was 30 degrees. I want to say it was 30 degrees just visually looking at that. Yeah, it was 30. So this is going to be our 30 degrees here. We've got our hypotenuse, we've got our adjacent, we've got our opposite there. Again, it's that SOHCAHTOA. We could rewrite that as well adjacently to it just to make sure that we don't mess up our sine and cosine. So if we're looking at the adjacent over the hypotenuse here, that's going to be the cosine theta, adjacent over hypotenuse. And I really encourage you to write out this just because it makes you make sure that you've put things in the correct spot. And then you can see like, oh yeah, the ft1 in the x-axis is related to the y in this context of this problem. When we're doing the theta relative to the x-axis, that works out nicely for both of these. And then we've got ft1 right there. And you can rearrange. ft1x is now equal to cosine 30 degrees times ft1. So whatever that is. And you can kind of imagine doing the same thing here, sine theta opposite hypotenuse, sine 30 degrees, because that is our theta. And now the opposite is the ft1y over the ft1. ft1y then is equal to sine of 30 degrees times ft1. So we've got a couple different things. We've got like the sines and cosines and these things related to each other. And we should then be able to relate them. So we've got the system of equations here. So I'm just going to grab that x-axis and bring bring that back down here, and we're going to now refer to this. These guys are going to be equal and opposite, but we now need to look at the ftx and do a little substitution here. So that is, whatever that is, that's going to be negative. Like the whole magnitude should be negative here of whatever this is in terms of the sum of forces. So I'm just going to put a negative out front there to account for that. And then we're going to have the same thing with the ft2 in the x-axis. And because these things are relative to the same angle, we're getting cosine for both the x-axes. So that should kind of make sense, which is in contrast to the last one where it was sine and cosine were different operations, but that was because the thetas were relative to different parts of the triangle. So whatever that is, that should have a positive magnitude. And these sum up to being 0. So you can do a little rearranging there and get that these things are equal and opposite to each other. We've got this cosine on both sides now. So you could imagine adding cosine 30 to both sides of the equation, and then you're left with these things being equal to each other. And you can, instead of having cosine 30 and cosine 45, we could write these out as decimal points. So we've got cosine 30. Do that as 0.8660 times ft1 is now equal to cosine 45. So what is that? 0.7071 times ft2. Now it's like, okay, well, let's figure out how much these are relative to each other. I'm trying to isolate for one of them. So if I wanted ft2 by itself, I'm going to divide both sides by 0.7071. That is going to end up simplifying down, but I can just kind of do a little guesstimation here. And that will be times the ft1. So I'm looking at that, it looks like slightly bigger than 1, that ratio. So 0.8660 divided by 0.7071 is going to be 1.224 times the ft1 is equal to ft2. I'm going to just do a little color coordination because it just helps you kind of see it a little bit where these numbers came from. So now that we have ft1 and ft2 relative to each other, we can then plug that into the y-axis. And this wasn't really necessary before because we knew that these things were equal to each other, and so we were able to just be like, well, they're equal to each other on the simpler example. But here, now it's like, okay, well, I have this system of equations, which is similar to what we were just looking at. But now we're going to have the m times g, so f of g should be mass times the acceleration of gravity, which should be a negative 9.8. So we've got the 10 kilograms times the negative 9.8 meters per second squared. So that's going to be the negative 98 newtons in this right here. So we've got the negative 98 newtons coming in there. Then we're going to have a substitution for the ft1 and a substitution for ft2. So that we can have those in terms of just like the tensions and then do a little substitution here. So ft1y is going to be sine 30 times ft1. And then ft2y is going to be sine 45 ft2. And that is going to end up having these so the ft2 is a little bit bigger than ft1. We'll end up seeing exactly how those compare. So we need to do a little bit of, we could substitute that fraction in at this point, but I think it might help us if we just see these as the decimal points that we've got. So if we've got our sine of 30 right there, that's going to be 0.5 times this ft1 is substituting for that part, and we still have the negative 98 newtons there. Just kind of add that in here. And then we're also going to have sine 45, which I think is the same as cosine 45, which should kind of make sense with those 45 degree triangles. So that, yeah, this is 0.7071 times whatever ft2 is. So this currently is close to what we want. These things are all kind of canceling out, but now we can plug in, instead of ft2, we can plug this in where ft2 is. So instead of having ft2 there, this guy right here, we're going to substitute that in with this and times that by the 0.7071. And then we've got all like terms, the ft1s, and we should be able to solve for ft1 as well. So let's take those two numbers. If we multiply those two together, maybe let's do that in orange. That times the 1.224. Let's just make sure that I did that correctly. 0.7071 times 1.224. I think it did come out, yeah. Okay. So we've got 0.865. Like, it's really 5 there if we round it to 4 sig figs, times this ft1. And we've got like terms with the two ft1s, so we should be able to combine those two like terms. So we've got 0.5 and 0.8655. So we've got 1.3655 when we combine those two times ft1, which was equal to the negative 98. If you were to think about that, that's kind of then being brought over to the other side. So we could write it out as negative 19 or 98 newtons. That's all equal to 0. Or we could just bring this over to the other side so that you've got the 98 newtons on the other side, which is now equal to whatever this is. This 1.3 something times ft. So we can see that ft is a little bit smaller than 98. So if we divide 98 by the 1.3655, we end up getting that f of t1 was equal to 71.7. I think that was 7, right? If we end up running it to 4 newtons. And so then it's like, okay, I have ft1, and then I could solve for ft2 as well, knowing that I have ft1. So we can end up plugging that number back into these other equations and checking that. So we've got that 71. It's like, okay, well, let's see what that ends up being. If we take that 71.77 and times that by 1.224. So got that right here. So that is what the force of tension 1 is. So ft2 ends up being times that by 1.224, 87.84 newtons. And then you can end up relating those to the sine cosine things that we were talking about earlier. So we can be like, okay, let's just double check the x-axis because they should be canceling out. But we can double check that now that we have 71.77 newtons. We can do that times the cosine 30. I think we actually already solved for the cosine 30. Yeah, it's 0.866. And that should be canceling out. So we've also got like, this is a negative. This whole thing should be negative. We do what is that? 71.77 times 0.8660. That's going to be negative 62.15. And then we've got the cosine 45 times whatever that was. So cosine 45 was 0.7071 times the 87 number that we got there for that tension of 2. So if we end up combining those, that should cancel out. And it does kind of look like that because 70% of that number should be around the 60s range. So 0.7071 times the 87.84. Yeah, moment of truth. Pretty close. I mean, it's off by the fourth sig fig, but I was rounding a little bit earlier, so that kind of accounts for that. If we had not rounded, then these should cancel out exactly. And so you can see the x-axis cancel out, and we could do the same sort of thing for the y and kind of see how much they contribute each to the y-axis. And that is totally doable. So let's just kind of take this guy right here for the y-axis and end up substituting those back in there. We got the 71.77 newtons and the 87.84 newtons. And they're going to be times by their respective pieces there in this equation. So just kind of replace them in here. Got that times this right here. And then that times that right there. And we should be able to solve for that. So 0.5 times 71.77. Yeah, it's going to be 35.885. Let's keep that blue though to keep with our color coordination that we've been doing. And that's kind of in the positive. And we do have 98 newtons, so you can kind of guesstimate what this other one's going to end up being. So we've got the 87.84 times 0.7071. Yeah, and then we've got our 62 number. And that does end up working out pretty close if we look at that. So if we end up combining those, that should end up adding up to like 98, which is, yeah, I mean, I'm seeing 97 point, yeah, it's basically 98 and you add those up. So they do cancel out. They're close to canceling out with our rounding that we did. So that's very closely related to what we saw in the original problem. You can kind of compare that to what we did originally, but those had slightly different sig or trig functions in the x and y axis, so you have to be careful. Here, there wasn't necessarily the same degree of, okay, let's work with the sine cosines for the substitutions, because we just knew that the y's were going to be equal to each other and x's were going to be equal to each other. So we had two of the same triangle. It was relatively easy to kind of work with that. Here, because we've got two slightly different triangles, but they're related through this proportion of their x-axes, you're able to see like, oh yeah, one of them needs to be a little bit bigger in the y-axis, and that would be the green one. And one of them is a little bit smaller, which is the blue one in the y-axis, meaning that this is a smaller tension and this is going to be a bigger tension. Whatever's kind of doing more of the y work ends up being a bigger force, essentially. So at this point in the video, you're probably understanding the strategy here and how that relates to the other problems. So you probably will see that like, okay, well, the sum of forces in the x-axis, well, they're canceling out because there's no movement there. There's no acceleration in the x-axis, so the sum of forces here in the x-axis should also be 0. So we do have, in this case, it looks like just the tension now, this Ft just going over there. So that's, I'm going to call it Ft1. And then we're going to have some other force now in the y. So if we think about doing our force diagram, you can see that the Ft1 is going this way, which I tend to think of as a negative. So we've got that Ft1, which is going to be some sort of negative number. And then we're going to have this guy, it's going up a fair amount at 60 degrees. So it's going up more than it's going to the side. And we can see that the its x component needs to cancel out with that force in the x-axis, so that they have no movement in the x-axis. If those forces cancel out, it shouldn't be moving. And then we've got this force of gravity just going down. That should be equal and opposite to this guy right here. because they'll end up canceling out in the x-axis now with that vector there. Knowing that, this problem actually is a little bit quicker than the other one that we just did. So we just kind of need to think about this now as plus the force of tension 2 in the x-axis. So if this is force of tension 2, then I would call this force of tension 2 in the x-axis and force of tension 2 in the y-axis. And they're going to be canceling out. So one of them's going to be negative, one's going to be positive. These are equal and opposite. So very similar to what we just looked at with those other problems. And then the y-axis, not too bad. We've got the sum of forces in the y-axis should also be 0 for the same reason there's no acceleration in the y-axis. And now we just have two forces. Now we've just got the force of gravity going down, and we've got this force of tension 2 in the y-axis lifting it up. Those should be now equal and opposite. So this just makes it a little simpler. So we know what f of g is in this context because it's a 10 kilogram weight. F of g is going to be mass times the acceleration of gravity, which is a negative 9.8. So we've got the 10 kilograms times that negative 98 or 9.8 meters per second squared. So we've got our 98 newtons for the force of gravity, which means now, because these are equal and opposite, that the force of tension 2 in the y, it needs to be taking care of all of that gravity. So it's the only thing pulling up at all. So this block needs that y component to cancel out the gravity to stop it from moving. So that's pretty nice. And then we can just kind of take a look at this triangle. And we could solve for the x-axis here, but it's not really necessary at this point. So I'm just going to ignore the x-axis, knowing that whatever that is at first, like we don't really need that for the ft2 if we're trying to find that. Now to get ft1, we will need that. Yeah, okay, good. So we've got this angle here. We've got the 60 degrees as well. And so we've got our SOHCAHTOA. I know I've been doing this for a long time. You might think I know what's what, but you can mess it up pretty easily. So I'd encourage you to write that. So if we're just relating at first this guy, the y, to the force, then we can think of that as my opposite over the hypotenuse. And so we're going to end up wanting to do our sine here. So if we've got sine of 60 degrees, that's going to be equal to opposite over hypotenuse. Or in this context of this problem, that would be my ft2y, which we already have, over the ft2. So I know that the ft2 in the y, that was 98 newtons. The unclear newtons, so that's an n there. And we've got sine of 60, so we can then relate that. So we've got 60 degrees, sine of 60, that's got to be 0.8660. And so this is about like 86% of whatever bottom number that is. So let's go ahead and take 98 and divide that by the 0.8660. Yeah. So I'm seeing that ft2 here should be slightly bigger than FTY to get that 86%. So this is like 113.6 newtons. If we're keeping this accurate to 2 sig figs, then we'd have to do a little rounding there. So that would maybe be like, what would that be? 110 newtons. If we're trying to keep it rounded to that degree of accuracy. So then if we want to do the this other tension, we've got to find the ft2y and then kind of plug that into this expression here. So we're going to need to do our cosine theta, which is adjacent over hypotenuse. So if we do cosine of 60 degrees here, we've got that now the adjacent is the ft2x over ft2. And we can solve for this. And we know what ft2 now is. Now I probably would not like use the 110 degrees here. I'd probably use the 113 because that's rounded a little bit too early. So I would just keep the raw unrounded number unless they told you to solve for this first, the y, and then solve for the x. You'll get something close either way, but it might just be a little bit more accurate in terms of the rounding to not use the other rounded number. We'll just use the raw number until we get to the final step. So we got cosine 60 here. 60 times cosine, that's just going to be a 0.5. So we can see our ft2 in the x is now going to be half of whatever that number was. So we got 0.5, and we take that and we multiply it by 113.6, and that should give us this top number. So we got, yeah, 56.8 newtons here. We could round that. That's going to end up rounding to being about, what was that, 57 newtons. So that would give you a slightly different number. If you'd done the 110, it would be at 55 newtons. So I would use the unrounded number to be accurate as we can until you get to a reported number here. So you could say now, like, okay, well, if I'm trying to relate these guys through here, that really should be what I'm doing before I'm doing the rounding. So I've got the one of these in a positive direction, so this would be 56.8 newtons in the positive direction. They're adding up to 0, and now you've got the ft1 plus that number, so ft1 ends up being a negative version of that, so that might be a negative 56.8 newtons, and then you might round that to the negative 57 newtons for that one. So these ones are essentially the same sort of logic where you're relating the x and y axes, and then through those relationships, thinking about how you can solve for unknown pieces and get those tensions. So it's very similar to the other steps. Luckily, though, there's no y component for one of these tensions, so the other tension has to take up all of the y component force to cancel out the gravity, and so it's just a little bit easier math, that type of problem. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.